Hello everyone, my name is Zachary Cronin, and today we'll be going through one of the most common hardness tests used in industry and academia, Vickers Hardness. As I go through this presentation, you'll notice some sources and links at the bottom of the pages. These contain additional details and more in-depth analysis of the topics covered, so please feel free to look into those if you have any additional questions or want a deeper understanding. Before we jump too far into this specific test method, I wanted to take a step back to go over what hardness is. In essence, hardness is the resistance of a material to plastically deform. This can also be related to other characteristics like resistance to abrasion and can sometimes be less directly linked to various mechanical and material properties like density and grain size. In general, there are three main types of hardness test. Scratch resistance, which involves a sharp object at a certain force normal to the surface of the material being moved in a parallel direction to that plane. You can see on the image to the right what the resulting deformation would look like, where a residual gouge is left behind. This test used the Mohs scale, which is developed to give a measurement of abrasion resistance in minerals. The next test we have, and the one we'll be focusing on today, is indentation hardness. Indentation hardness gives a direct hardness measurement, generally in terms of compressive force applied in an area of deformation. However, the units aren't intuitively represented and are usually unique to the test performed. Due to their ease of use, inexpensive cost, and useful information, they are commonly used in various industries such as automotive, aerospace, structural development, and mining, and multiple tests have been designed, like the commonly used Rockwell, Vickers, and Newt. In the image to the right, you can see the kind of indentations left by these tests, the first being a pyramid-shaped indent from a Vickers test, and the second being a spherical shape from a Brinell test. Lastly, we have rebound testing, which is also known as dynamic testing. This is a little more specialized towards the relation of hardness to elasticity of a material and involves dropping a probe that bounces off the surface of the specimen. If you ever hear of Leib's hardness, this is the type of test it is referring to. Vickers Hardness was developed by Robert Smith and George Sandland in 1921 at Vickers Limited, a company dedicated to steel and forging that later moved on to engineering the fabrication of ships, cars, and aircraft. They had a need for a replacement for the legacy hardness test method, Brinell, which relied on a steel ball as the indenter. This steel ball was able to be deformed during testing, reducing the accuracy, and did not have a standardized size, meaning the calculations had to take the probe's diameter into consideration. Vickers introduced a standardized angle, making the size of the indenter independent of the calculation, and chose diamond as the probe material, so the tip deformation was significantly reduced as an unwanted variable. Vickers is great for testing most materials, although it is generally preferred for harder materials since only a single load is applied. While it permanently deforms the area it is probing, the indentation is so small it is often considered a non-destructive test. Because it is over 100 years old and has been commonly used throughout its life, it has the benefit of a wealth of available data online in industry and in literature for you to refer to. The Vickers instrument works by applying a compressive force onto the surface of the sample with a square pyramid diamond indenter, as we can see in the image to the right. This plastically deforms the material by permanently displacing the atoms that it interacts with, and the resistance of the material to being deformed is measured by comparing the size of the indentation and the force required to create it. The load and dwell time are controlled by the individual performing the test prior to the application to the sample, and most equipment can apply loads anywhere between 10 grams force to 1 kilogram force, with some macro Vickers going all the way up to 30 kilograms force. It is important to be able to vary the load applied because even though for many materials the hardness is independent of the force application value, some have unique properties that cause their hardness to be influenced by the magnitude of load. Also, materials may simply respond better to higher or lower loads. For example, a polymer would likely not need nearly as much force applied as a ceramic to get a measurable indent. As previously mentioned, Vickers values are independent of the size of the tip as long as the angular geometry is maintained. This makes calculation of hardness values much simpler and allows researchers to change out indenters without needing to recalculate equations or reprogram any equipment or software. In the lower image, you can see a square pyramid shape of the diamond tip. where the angle of the four sides consolidate is strictly controlled. The indents left in a material generally have a depth of 0.1 millimeters or less and need a lateral dimension of 20 microns to have confidence in the measured value. The final value from this test is usually represented as Vickers pyramid number, or HV, although it may be less commonly referred to as diamond pyramid hardness, or DPH. If you would like to see the operation of Vickers Hardness machine, I encourage you to go to the link in the footnote where the second image is referenced. It is a great video where channel Material Science 2000 shows all of the steps from placement of the sample to the automatic hardness calculation in about 2.5 minutes. Vickers hardness is usually performed in accordance with ASTM E384 or ISO 6507, both of which outline the indenter, measurements, and calculations for the final value. As I had mentioned, the geometry of the tip angle is strictly controlled for Vickers. It is a fairly shallow square pyramid tip with each face having an acute angle of 22 degrees from the base, which leads to 136 degrees at the point of the apex, which we can see in the diagram to the right, representing the tip indenting into the substrate. The residual indent left behind in the sample can be viewed as a two-dimensional square where the cross values D1 and D2 are measured in millimeters. Because the angle is fixed, we can use the D values measured to find the area of the indent and divide the force applied by that calculated area to give us the HV number in kilograms force per millimeter squared. Through some trigonometry, we can calculate the area of the indent by dividing the square of the D value by 2 times sine of 68, where D is the average of the D1 and D2 values that we measured earlier. Since 2 times sine of 68 is constant, it'll be often represented as 1.8544 for an approximation. Once we have the area, we can divide the force applied in kilograms force by it to find our hardness value, which resolves to the highlighted equation of 1.8544 times the force divided by the average cross distance squared. For most bulk materials, the hardness value is constant. Therefore, the force applied is a direct proportion to the area of the indent, or the square of the cross length. Meaning if you applied a 500 gram force load followed by a 1.5 kilogram force load on the same material, you would expect a 9 times longer D value. A word of caution though, as there are some materials that have other influencing factors that may interfere with this relationship, especially if the applied force is excessively low or excessively high. As a side note, some equipment measures in newtons, in which case it is relatively easy to modify the equation as seen in the bottom right to accommodate. For those of you interested, I didn't see any sources online or in literature on the actual derivation of the area equation based on the D value. So I went ahead and derived it here. I don't want to spend too much time on it, but feel free to pause here and work through the steps if you want, and just note that the pyramid is not to scale. Now that you've calculated your Vickers hardness value, it is time to report it. Well-known materials that have gone through innumerous tests may only have single numbers representing their Vickers hardness value, but for individual tests, it is reported in a specific fashion. For this example, we are going to use 600 HV 2030. 600 is the hardness value that would have been calculated on the previous slides. The letters HV signify that this test was done in accordance with Vickers hardness. The 20 following the HV is the load in kilograms force. And finally, the number following the slash is the dwell time in seconds, in this case, 30 seconds. If the dwell time is between 10 and 15 seconds, this number is often omitted. Here are some common hardness values from Vickers testing. We can see that metals generally range on the lower third of common hardness values, which is roughly up to 3,000, from soft tin to much harder tool steels. Ceramics are generally much harder than metals, with values regularly more than double that of some of the hardest metals, which is why we can see the Brinell test using a steel ball would have insufficient ability to analyze them. Polymers, on the other hand, fall on the lower side of the scale, and sometimes are difficult to measure due to their high elastic properties, such as rubber. For reference, diamond is also included here with a value of 10,000. This is so that we can see why it is used as a probe, and it is highly unlikely for the sample to be able to deform the tip in any meaningful way. The instrumentation of a Vickers hardness tester is fairly simple, though they can vary drastically depending on the features and level of autonomy chosen. On the right, we see some of the important pieces labeled, but at a minimum, it must have a stage, an indenter, and controls to choose the force and the dwell time. Some of the key parts of a modern Vickers include the eyepiece, which along with the objective lenses, usually 10 times and 50 times, allow for preparing the sample, placement, and indentation location, as well as measuring the indentation dimensions. The indenter is often detachable, allowing them to be replaced, and with some more advanced instruments, the indenters for other hardness testers may be inserted instead. A revolving turret allows for the transition from optics to the indenter at the same location so that the individual performing the test knows exactly where the indenter will be applied. Similar to exchanging indenters, some instruments may come preloaded with alternate indenters on the turret, allowing for quick testing with multiple different methods. The stage is where the sample is rested for testing and comes equipped with lateral and height adjustments, and sometimes tilt adjustments as well. Here we have the basic analog version of a Vickers hardness tester. It gives the analog readings of force and dwell time, and the user is required to calculate the hardness value themselves. They often come with a microscope with at least one magnification. However, the least expensive can be as low as $3,000 without any microscope integrated, meaning the measurements would have to be done on another piece of equipment. Alternatively, more modernized Vickers hardness testers have digital interfaces, whether directly integrated, like the equipment on the previous slide, or connected directly to a PC similar to the Blue Star model to the right. This allows the setup, calculations, and data storage to happen relatively autonomously, with the researcher only responsible for the sample setup, parameters, and marking the corners of the indent. Since the instrument already knows the force and dwell times input, once the D value is determined, the hardness value is generated along with any associated images desired. While the two types may have a relatively significant price difference, they both require the same style of indenters, which usually run around $1,000. Vickers hardness is readily used in industry, especially as a quality control tool, but it can also be key in finding the next generation of materials. For example, in Gerbuz et al., where the effects of sintering time, temperature, and graphene nanoplatelet concentrations on aluminum composites are explored. As you probably know, aluminum is extremely common in the aerospace and automotive industries due to its preferred strength-to-weight ratio, manufacturability, corrosion resistance, and non-toxicity, unlike materials like cadmium or chromium. Unfortunately, its strength and wear resistance can be a limiting factor for some of the applications where it would be desired to be included. To overcome this, research is being done into designing aluminum matrix composites with dispersed graphene nanoplatelets to increase the strength and hardness of the material. The manufacturing process is similar to many ceramics, where the aluminum and the GMP powders are mixed into a slurry with 0.1, 0.3, and 0.5% concentrations by weight of graphene nanoplatelets seen in the table below, ball milled and filtered, then dried and compacted to a green state cylinder with a diameter of 130 millimeters and a height of 30 millimeters. Once formed, it was sintered for variable temperatures of 550, 600, or 630 degrees Celsius for variable times of 60, 120, 180, or 300 minutes, also referenced in the table below, for a total of 24 different combinations of tests. So here we can see the sintering conditions compared to the density, measured by the Archimedes method, of the samples for each concentration on the top two graphs, and the concentration compared to the HV for each sinter time and each temperature. Both the highest hardness and density values peaked at 630 degrees Celsius sintering temperature, 180 minutes of sintering, and 0.1% concentration for each set of variable combinations. While the initial GMP inclusions increased the desired properties of the composite, further increases led to agglomerations that reduced the ability of the aluminum to interact with the graphene, leading to porosity, weakening the material. Increasing the sintering time increased the grain size while simultaneously decreased the porosity of the sample. Around the 180-minute mark of sintering, the rate at which the grains grew increased to the point where the reduction in hardness that it caused outpaced the increase from the reduction in porosity. This decreased the overall hardness of the sample. Lastly, there was a fairly direct correlation between increasing the temperature of the sintering process and an increase in the density and a significant increase in the hardness of the sample. It was proposed that this higher temperature provided the energy needed to allow bonds between the aluminum and the graphene nanoplatelets, strengthening their interaction. This research shows how Vickers hardness can be used as a great preliminary test for the insight into the mechanical properties of novel materials which may impact future industries. Vickers is a great and versatile indentation test, being non-destructive, inexpensive, and easy to use compared to many other characterization techniques we use as material scientists. For general purposes, there are no special sample preparations, vacuums, temperatures, or conductivity requirements needed, and nearly any hard solid material can be tested. The range of values it can offer is quite wide, more encompassing than most of the other tests, and it can accommodate these with a wide range of applicable loads. The diamond tip provides very precise measurements, and the hardness value can often be converted to other common hardness test values, for example, Rockwell C. Because it is so common and other indentation test values can be converted to Vickers values, there is a plethora of available values and data easily accessible to compare results to. Although such a versatile test, there are still situations where other tests may be preferred or may be insufficient in providing the desired data. The square tip may produce cracking on brittle materials, even going as far as complete fracture. Noob hardness is often used to alleviate this potential issue by utilizing an elongated diamond tip. Some samples behave differently under different loads or dwell times, which may make the data unintuitive or add difficulty to material selection for various applications. The indenter requiring 20 microns makes it too large to measure features smaller than that footprint, requiring a nano indenter instead. Measurements in dwell times make it slower than methods like Rockwell that only measure loads and displacement. And the computation and tip often make it more expensive than these other methods as well. Samples must also be thick enough, or else the stage may begin to influence the results of the test, similar to how an overly rough surface may affect the value as well. Lastly, softer materials and materials with higher elasticity do not give consistent or accurate values, as the indent can be unreliable. I've mentioned that Vickers is considered a non-destructive test and it is easy to use, but it is important for one to familiarize themselves with both the test and the material they are testing. In the images to the right, you can see one of my first attempts at performing Vickers hardness for an undergraduate lab project in an attempt to compare the hardness of a glaze to the underlying ceramic. I selected a force value much too high for the specimen, shattering the ceramic in a brittle fashion, leading to the importance of having a general idea of the material you are working with and the general range of forces that can be applied to it. To summarize Vickers hardness, it is a method that can provide a wide range of hardness values for diverse materials. The value it gives is a property of the bulk material, and it does this through the mechanical indentation of a diamond pyramid probe and comparing the force applied to the surface area of the indent. It is a non-destructive test that is more accurate than other indentation tests in exchange for being a more expensive piece of equipment. I hope you were able to acquire some useful information from this presentation, and I appreciate your attention. Thank you.